So last time we started talking about nodal analysis, and we saw that nodal analysis is a very powerful tool. Now, it's powerful for a variety of reasons. One of the reasons, the primary reason for it is that, of course, it's a way of solving any circuit problem. Anything that can be reduced to a connection of branches via nodes and things of that sort can essentially be solved with the nodal analysis. It is the most powerful tool we have. Now, it's valuable for that reason. And as you saw, and as we'll see more today, it's mechanical. It's a mechanical tool. So the good thing about a mechanical, something that's very systematic, algorithmic, you could call it mechanical, quote unquote, is that if you follow through the steps, you don't have to think about what you're doing if you follow the process. That's also a bad thing, depending on. Now, if you're a computer, that's a great thing, right? Because you can follow a procedure. And that's exactly what computers use, what computers do to analyze circuits. Basically, any of the circuit simulators you may be familiar with or you may have heard of or you will hear about are, the classic example is SPICE and its derivative. Now, a lot of computer programs are named different things that are based essentially on the SPICE. Is essentially a way of, when you type in a circuit, when you type a network for it, what it does, it converts it to that matrix representation. And now, depending on what kind of analysis you want to do, it does the nodal analysis either once or multiple times in different ways. For example, if you want to see the large signal nonlinear thing, we saw that nodal analysis is a linear thing. What it does, it linearizes it around a point. So it calculates the operation point, where the operation is. It linearizes the circuit around that point. It makes it take, say, okay, if the circuit were linear around that point, if I look at the nodal analysis, how much, which way would it go? So it looks at it, it takes a small step and sees if the step, if over that small step, there are not huge changes. If there was large changes, and you define what huge or large means, it shrinks the step till the changes become incremental. And say, okay, so that's the next step. Then again, finds a new operation point, redoes the nodal linearization around that new point, does the nodal analysis, keeps going, repeats the nodal analysis. And it's a good thing because because computers can deal with matrices very easily. Now, so what was the process? Again, if you remember, so the first step was to define a reference potential, aka ground. The next step was to define voltages with respect to that. So that was the way it was different about branch voltages. So you define the node voltages with respect to that ground node. The third step was basically what you did was to write, and this was a critical step, you wrote KCL for each one of the nodes in terms of node voltages. And to write KCL in terms of node voltages, you have to use Ohm's law. And that's where linearity comes in, right? Because KCL is written originally in terms of currents, right? To write it in terms of voltages, you assume that everything was linear, so you use Ohm's law, you converted those voltages those currents to voltages, essentially, wrote it in terms of voltages, and then it created a set of equations. We solved those, and we will see more of those today. So that was the basic procedure. Now, so just to refresh your memory, let's complete the example we did last time, but we'll do it more quickly. So this was the example we started with last time. So this is an example. I mean, we didn't complete this example, but I'm going to take you through it one more time to refresh your memory and see what it does. So this was R1, 4 ohms, R2, 2 ohms, R3, which was 2 ohms. There was a current source here too. Let's call this I4 for 4 amps. R4 for 3 ohms. R5 is 2 ohms. I3 is 3 amps. This current we called I2. And it was 4 amps. And this is I1 for 11 amps. Okay. So that was the statement of the problem. Now, if you wanted to do nodal analysis, we can do it together right now and in the class. So which node would you define as a ground? Probably, I mean, it doesn't matter really, but to make your life easier, rule of thumb, which one would you define as ground? This one, because it has the most connections, right? So I would define this as ground. And when I do this, it means that all of these things are essentially ground. This can be equivalently drawn with this line removed and a whole bunch of grounds connected here. And that's a common notation you will see, particularly when you're dealing with electronic circuits and things of that sort. That you don't show it this way. You don't draw this big line. You just remove that, and you have ground, 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 ground. Just for the change, I mean, today, since last time we did it that way, let's do it this way. So you get used to it. So what this really is, you can do it this way, this way. They're all grounds. You can even do it this way if you want, which is the same thing, essentially. So this is the same circuit. We're just showing, using a symbol for showing that one node, that reference node, the ground. OK, so now we need to define voltages. So how many more nodes do we have in addition to ground? How many do we have? 3. So we call V1, V2, and V3 for the 3 nodes. And then we need to write KCL in each one of them. So we could do that. But also what we can do is that we saw that as far as we are not worried about dependent sources, we could do this by inspection. So let's this time do it by inspection straight from the beginning. So let's do that. Let's write the Y matrix. So this is your Y matrix that gets multiplied by the V vector, the voltages of the nodes, to give you the stimuli vector, IS. So this is IS, this is vector V, and this is the matrix Y. So what are the diagonal terms? Let's go around the class and quickly just answer the question. Maybe we can start from somewhere so we can everyone can answer it. Maybe we can start maybe on that side. No, sure. So you remember, you don't remember, OK, so if you remember the diagonal terms where the sum of conductances attached to a node, to the node of interest. So the 1, element would be sum of the conductances attached to this node. So what is that sum? So this is this one. What is, so the associated conductance we can show as G1, right? So it would be what? G1 plus G2, exactly. Now, how about this node? Now, why don't you continue on that? So the second diagonal term, for element 2, 2, which associates with node 2. Exactly. G2 plus G3 plus G4. And now that you're doing the diagonal terms, you're on a roll. So let's do the last one. 3, 3. G4 plus G5. Exactly. All right, good. Now for off-diagonal term, maybe we can go to the next person. So what were the terms associated with the off-diagonal? Conductance that connected between the nodes 1 and 2. What is that? With a minus sign. So what is that? Minus G2. And we saw that in case of no dependent sources, this is going to be symmetrical, obviously, because the conductance connected between this node and that node is the same as conductance connected between that node and this node. So it's going to be negative G2. Here, how about this term? 1, 3. 0. There's no explicit conductance or resistance attached between them. Now, how about these nodes? 2, 3s? Minus G4, exactly. We are not done yet. We have to also specify the stimuli vector. We said that in our convention, these were what? These were currents, if you want to do it by inspection, these were the currents injected into or going into the nodes. So let's start with the next person on the row. So what is the first term for node 1? Could you, yeah, that's fine, but specify it in terms of parameters for now. I1 minus I2. Exactly. And then second term? Negative 4, exactly. And then last one? I2 plus I3. Thank you. So at this point, this was easy because it didn't have any dependent sources. So at this point, it's basically, we have specified the problem. We have converted the problem to a mathematical problem. Essentially, we've stripped it of all of the interesting physics associated, all the crazy things that can happen, you know. So we just reduce it to a mathematical problem, which is an important problem. It's a linear algebra problem, but it's a mathematical problem nonetheless. So we can actually write this in terms of, in numerical forms, right? So let me just quickly do that. In numerical terms, since there's nothing exciting or interesting about that, I do it myself. I'll keep the exciting things for you. So I'm just like replacing those G components with their actual value, right? And check my work because I am known to make mistakes. Unintentionally most of the times. And then negative G2, so which is negative 1/2, and 0 is 0. Negative G4, which is negative 1/3. And, you know, I'm dropping units. I shouldn't be doing this. These are all Siemens or 1 over ohms or muos. You know, some people show that 1 over ohm is upside down ohm or Siemens. So either way, but I'm dropping the units. But the final answer, I mean, it's okay in the matrix to drop the unit. So we'll indulge ourselves in that, but not a lot more than that. Keep the units. You're engineers. It's very important to have the units. Yes?
I noticed that, like, in the textbook about the independent source, or dependent sources, it would say that like the current source was proportional to the voltage of something else, and it would just not pretend that the units weren't an issue.
Right. So you're talking about. So your question is about when you have in many examples, for example, sometimes you see cases where there's a dependent current source and they just basically ignore the units. Where there's a current source that depends on a voltage or a voltage source that depends on a current or something like that. They ignore the units. It's not a good practice. It generally, for those cases, you need to really state it. For example, when you're talking about a transconductance, when there's a voltage-dependent current source, we really use the transconductance and usually show it. In electronics, that happens a lot. And when you talk about transistor circuits. And you show it with millisiemens or Siemens. Usually it's millisiemens for transistors and things of that sort. Or millimuo, or the older literature basically uses muo, which is upside down ohm and also backwards ohm. But you need to keep the units. So in general, but you know, sometimes when you're writing a matrix, just carrying all these like Siemenses doesn't make life a lot easier. So we just basically say, oh, everything is in Siemens for now. We keep track of it mentally. But in general, obviously, it's a good habit to have the units there. Any other questions? All right. So now, it's this thing times the V vector, which is now the stimuli vector, which is I1 minus I2, 11 minus 4, which is 7. Now, negative I4, which is negative 4, and I2 plus I3, which is 3 plus 4 is 7. Right. So that's the thing. If you want to get rid of these fractions, what do? You can always play this trick with matrices, right? You can multiply each row, including the right side, by any fixed number, and it wouldn't change the answer. Why is that? Yeah, exactly. So each one of these lines defines one equation, right? So if you multiply both sides of the equation by some number, that's fine. So you can multiply one equation by one number and the next equation by a different number. And still it will be the same equation. You want to make your life easier. So you can actually do that. You can say, okay, find the least common denominator between these two. So I multiply this by 4. I multiply this by 6, I guess. And I multiply this by 6. Right? Would that work? So that way I will get a new problem, a little bit more straightforward. So 1 plus 2 is 3. I get a negative 2. I get a 0. I get a negative 3. I get a 3 plus 2. So it's 6 plus 2 is 8. I get a negative 2. I get a 0, negative 2. I really didn't need to do any of these two because they were already sitting there. And there's some problem here, obvious. No, it's not a problem here. Never mind. This is not going to be symmetrical anymore because I'm multiplying it by different numbers. So it doesn't have to be symmetrical. And this is going to be a 5. It's a 2 and a 3. Just check my calculations. If you see anything, tell me right away. And also we have to multiply these by the same numbers. So this becomes 28. This becomes negative 24. And this becomes 42. The multiplication table. It's interesting. So it's a completely unrelated, kind of very tangential anecdote. There are some people with brain injuries that certain parts of their brain gets damaged, so they can't add, but they can still multiply. So they're done by different parts of your brain, because actually multiplication is more memory, at least in small scale, and but addition is something that you actually do in your head apparently in a different way. So it's neither here nor there, but it's interesting. Okay, so we have our mathematical problem in its most general, in the form that's numerical. So from this point, it is more of a just basically matrix inversion, but we'll do this one just to make sure that everyone gets more practice, and I will enlist your help. So how do we invert a matrix? So the matrix we are trying to invert, I'm going to rewrite it here. It's 3, negative 2. Can you read it to me because I'm getting reflection off of it? I can't see.
3, 8, negative 2.
Negative 2.
0, negative 2, 5.
Okay, yeah. That should be a 0. Negative 2, 8, did you say? 5. It's just completely invisible. Yeah. Okay, so that's the matrix we are trying to invert. So this is our Y matrix, or modified Y matrix really, because we multiplied it by some numbers, so we have to be careful about that. So from a procedural perspective, so we are inverting this, so we have to calculate the well, the first thing you calculate before you try to even invert something is what? To see if it's invertible or not. The determinant, right? So first thing you need to calculate is the determinant of this matrix. So you can show it this way, or you can just say explicitly determinant. So what is the determinant of this thing? It's this number times the determinant of that. What is the determinant of this guy? It's 5 times 8, 40, minus 4 is 36 times 3, so it's 3 times 36. Now, and then you have this, so it's minus that guy times the determinant of these 4, which is negative 15 minus 0, negative 15. So it's negative 15. So this is 30 minus 30. One of the 36 is minus 36. The other two give me 72, so total is going to be 78. So that's the determinant. Now I have to, so it is invertible because the determinant is not 0. And remember what determinant was, right? We talked about determinant, what the meaning of determinant is. It's basically the ratio of the area or the volume of a unit cube when it goes through this transformation to the original cube, or basically the area of the resultant shape when you apply this to a unit cube, a 1 by 1 by 1 cube, or in general an nth dimensional hypercube. Okay, so now the next thing we need to do is just to calculate the cofactor matrix. So now this is the part where I'm going to enlist your help. So who was next in line? I guess you. So how do we calculate the cofactors? What's the first cofactor?
So you remove the first row, the first column.
Right. So for element 1, 1, you remove the associated row and column. What is left is?
36, or like 8 times 5.
Yes, so the determinant of what is left, which is 36, times, we have to be careful about this negative 1 to the power of m plus n. In this case, m plus n is even, so we don't have, so it's positive. So it's going to be 36 here. Now let's continue through it. Maybe you can do 3 and then we'll give other people a chance to. So the next one, this cofactor, how do we calculate it?
You remove the first row, the second column.
Right. You remove the first row and second column. So you're left with these 4. And what is the...
So it's negative 15, but you have to multiply by
Yes, negative 15, but you have a minus sign because this is an odd sum. So basically it becomes 15. How about this one? The cofactor associated with this cofactor? You remove this line and this row and this column. You're left with this. What is that? 6. Yes. And no minus sign. OK? So next row, maybe you can help me for this cofactor. What do we do? Eliminate this row and this column. You're left with these 4 numbers.
So it's -1 because like -1 n plus n.
OK, so the -1, yes.
Times -10.
-10, so it's going to be
10.
10. Thank you. And then we go to this cofactor, the one in the middle. So we remove this this column and this row. So you're left with these 4
So 15.
elements. Yes, 15. And then for this one, we remove this and that. You're left with these 4.
So -1 times -6.
6. Thank you. Everyone follows what you're doing, right? Should be very clear. If it isn't, raise your hand right now. Or forever keep your peace. OK. OK, so next row. So here, this cofactor. How do we go about that? Eliminate this and that. This is what you're left with. So what's the determinant of this matrix? 4. And is it going to be positive or negative? Positive. So it's going to be 4. Now how about this one? This cofactor. We eliminate this and that. So we are left with these 4. What is that determinant first? -6. This times that minus this times that, which is -6. And then there's a minus sign here, which gives you 6. And then the last one, this guy, is the determinant of this times. So what is the determinant of this? 3 times 8 is 24, minus 6 is 18. But what, with a positive or negative sign? So positive, yes. So it's 18. OK? Very good. Let me just double check, make sure we haven't made any mistakes here. OK, good. So now, so how do I invert the matrix? What is the inverse of the matrix? Yes? Cofactor transpose. This is the cofactor. Cofactor transpose means that you flip them with the mirror, the diagonal being the mirror. So they flip this way. So the inverse of that Y matrix prime is going to be, I'm going to just write that it's going to be C transposed over the determinant of Y prime, which is going to be what? 36. I'm sure you can transpose a matrix, so I'm not going to ask you. I keep the easy ones for myself and the hard ones for you. You get to do that once you're the professor. Something to work toward. All right. OK, so that's our inverse. I mean, you can try to divide this by that and see what they would be, but it's better to write it this way. Now, if I want to calculate my voltages, V1, V2, V3, what do? I just multiply this inverse by the I vector, the stimuli vector, right? Which is going to be 1 over 78 times this matrix times the stimuli vector that we created, the new one, 28, negative 24, and 42. So you know how to multiply this. Again, it's one way to think about it. This row times this column, they add. This row times this column, 1 by 1 multiplied and adding, multiplied and adding. You get 3 numbers, right? And then, of course, you scale it by 76. When you do that, again, I'm not going to do the just basic calculations here. It's going to be 12, 4, and 10 volts. So when you do that calculation, then you can verify that for yourself. You get these numbers. So you can see, again, it solves anything. Now, somebody asked me a good question last time in the, over the break, last lecture, which was, yes, but you know, what is the point? Why don't you just invert the matrix, or why don't you just calculate the inverse of the matrix the other way around, or there are other algorithms and all those things? What's the advantage of writing it this way? The advantage of writing it this way and keeping it this way, in addition to being able to handle it with computers and all those things more easily, is that it also is a tool, as we saw last time, and we'll review it today quickly, that it's a tool for calculating and coming up with new results, not only just numerical ones. It's a tool for proving theorems or gaining just deeper understanding of this thing. So it's a framework for you to think about things, not just a method of solving problems. And we'll see that, I mean, we saw the example in the case of existence. Now, of course, if you have dependent sources, you have to include them, and they would add new elements to these matrices. So if I threw in a new dependent element somewhere into this example, let's see what's going to happen. I mean, we talked about dependent elements before last time, but I just want to make sure that we review it because this is an important concept. So let's say I throw a dependent element here. Well, let me use a different color. So let's say I put a dependent current source here, which is proportional to this voltage. So this is going to be basically 2 times V1, so the current. Obviously, the units of 2 are Siemens, or 1 over ohm, because it's converting a voltage to a current. So what it says is that this current, you can call it, I don't know, I5, is going to be dependent on that. So now let's see how it's going to change our equations. Which KCLs would it change? Would it change the first KCL for this node? No. So this row is going to be intact. Would it change the second KCL associated with this node? No, it's not going into that node, right? The middle node. Would it? So it's not going to affect that either. How about that? So it better change something. So the answer must be the third row, right? So it must do something here, otherwise it would be in trouble. So what is it going to do? So think about that KCL. The KCL that resulted in this, there were 4 currents before we had this, right? There was the current through this path, which was a V2 minus V3, right? Which is reflected by presence of G4 here and there. V2 and V3, right? The current leaving this node really is V3 minus V2 times G4, which basically gives you a positive 1 here and negative 1 here. So these two came from this current. Now, what came from this current, the current through this resistor R5? G5. Where is the effect of these two currents? Here. Because this is the last equation, right? So what am I adding? I'm adding an extra current leaving the node, right? Which is what? What is that current? Let's call this a capital GM instead of 2. And the value of GM is 2 Siemens. Let's make it parametric because everything else is parametric. Right? So if I add that, so now what term would that add to my equation for the currents leaving that node? What is that term associated with that purple current source? Who's the next person? Yeah.
You mean like in the matrix?
In the equation, or in the matrix. So I was just trying to give you the intermediate step, but if you want to give me what the final result is, that's fine too.
GM in the first column.
Exactly, a GM here. And why is that? Because this current, so the sum of these 5 currents needs to be 0. So this current is going to be GMV1. So it has to be something that comes from this column, which gets multiplied by this V1. Because this goes like that, right? So then this has to be a GM, as you pointed out. So this gets modified to an asymmetrical one, but nonetheless, it's again the matrix that now it will be a different matrix. So this is the change in the matrix. It's a different matrix. You have to invert a different matrix if you needed to invert it or not, or keep it that way. But you can see that it's mechanical. That's why computers can do it. Because you define a net list, and it basically says, OK, well, I put the current here, I put the GM here, I put this, and then calculate. OK, so that was for that. And then we saw the last thing we also saw last time, the other thing that we saw last time, which was quite important, was the existence, the condition for existence. And we talked about this, so I'm going to just quickly review it for you, is that we saw that since the equation we are trying to solve is this equation, right? And we are trying to solve solutions for that. Now, we know we have to invert a matrix. Yes?
Yeah, I have a question about the method.
OK.
The whole inverse micro-package thing on the homework and the test, can we do the other methods like Gaussian elimination?
You can invert the matrix any way you want. So the question is that on the tests, can you use other methods? Absolutely. If you're given a numerical matrix, I don't care how you calculate it, as long as you calculate it. And on the test, probably you shouldn't use calculators for doing the whole thing by itself. You're welcome to do it anyway. But if it's the correct answer, it's good. If it's not the correct answer, not so. Yeah.
So reducing the matrix is fine too.
If you can find I want you to find the answer to that.
Get the answer.
Yes.
Legitimately.
Right. Yes. Yes. OK. Any other questions pertinent to this question? All right. Let's go back to this. This must have been a really pressing thing to know what the test, how the test is going to work out. OK. So for the existence, we talked about solving this equation, right? So what we are trying to do is to say basically, look, we are trying to solve for V, and the way we solve for V is basically we invert the matrix any way you like. And this is IS, the stimuli, and you multiply it. But OK, so that's for that. That's OK. But now we wanted to see when does it exist. So we know when does a solution exist and what does it mean in circuit domain. Obviously, we know when from a mathematical standpoint, when does a solution exist? When the determinant of the Y matrix is non-zero, right? And you see later on that the determinant of Y matrix is important in a lot of things. For example, when you get to frequencies and natural frequencies, you will see that the natural frequencies are the roots of the determinant of the Y matrix in a circuit. So the determinant of Y matrix plays an important role in things. But we are not there yet. So we'll see. So what happens is that obviously if the determinant of Y is non-zero, then you have a solution. But we want to see what does it mean in circuit domain. And we saw last time, and I'm just quickly going to remind you, is that you saw that if this is 0, if and only if, the only solution for Y times V being 0 is V equals 0. So in mathematical terms, if the only solution to this is this being identically 0, then this is true. So what does it mean? It means that if you look at a circuit, you get rid of all the stimuli. You use null also. So what this means is this is equivalent to saying null all the stimuli. Or in other words, all the independent sources. Now, you will hear this phrase, null the independent sources, a lot. Again, it will be clear what it means. What does it mean? So if you have a voltage source, what does it mean? When you say null it means set its value to 0. But for both of them, it means that set its value to 0. What is it for a voltage source? Short circuit. What is it for a current source? Open circuit. So when you say null the independent, all the independent sources, that's what it means. So when you null the independent sources, and then you should see a circuit which guarantees every node has a 0 voltage. If there are nodes there that can have any voltage other than 0, then it means that this is not That's a singular thing. That's a singular circuit, and you can't solve it this way. It means that the determinant of y is 0. And I gave you an example last time, which I'm going to repeat very quickly here, which is, so this was I1. This is going in the other direction, I1, R2, R1, right? So there are 3 nodes, V1, V2, and V3. If I assume this to be ground, I could do it for the other one. And in this circuit, when I null the independent sources, it means that for current source, they would become open circuits. So they would go away. And you can see that V1, voltage V1 is identically 0 because it's connected by a resistor to ground, and there's no current through that resistor, so this voltage drop should be 0. So this voltage has to be the same as that. But you can see that all you can say about V2 and V3 is that they're equal. But it doesn't tell you anything about them being equal to 0. They could be equal to any other voltage. And that's exactly an example of something. And you will see other examples in your problem sets. OK, so this is as far as we went last time. It was a long review, but I thought it's an important one. Now, there's one more thing that we didn't talk about. So it's, a good question was asked towards the end of last lecture. Yes? Oh, yes, yes. I'm sorry. Yes, absolutely. Thank you. I wrote it incorrectly here. The determinant is non-zero because that's the condition for being non-singular. Thank you. So the condition is that this comes from, if you want the determinant to be non-zero, in other words, for a solution to exist. So this means solution exists. This has to be true. If you want to make it even more mathematical, you can write it this way. Yes?
Wait, so for this example circuit here,
Mm-hmm.
you're saying that is true because you don't know what V2 and V3 are, right?
No, so what I'm saying is that since this is not true,
Right, okay.
then it means that the determinant is 0.
0, okay.
Right? It's an if and only if. So if this is true, this is true. If this is true, this is true.
Okay.
Since this is untrue, then this is untrue.
Right, we cannot say that's true for this circuit, right?
No, we can say that this is untrue, which means that the determinant is 0. We actually did the determinant last time. We wrote, if you remember, the Y matrix was G1, 0, 0, 0, 0, I think G2, G3, negative G3, G negative G2, negative G2. So that's the Y matrix for this, whose determinant is 0. Yes, thank you for that clarification. Appreciate it. OK, any other comments or questions? No? All right, let's move on. So there was a question asked last time that, OK, fine, but what if you have voltage sources? Everything you gave us conveniently had current sources. What if you have voltage sources in there? What do you do with those? OK, that's a fair question. That's a good question. Let's start with an example and see what happens. So the example I'm going to use here is, let me just write my example here. I'm going to put the numerical values here too. R2 of 8 ohms, R4 of 4 ohms, and R3 of 6 ohms. This voltage is 5 volts, and this voltage is 10 volts. Let's call this V1, capital V1, and let's call this V2. OK? So I think we have all the parameters that we need. All right, good. So how do we deal with this? Let's go through our procedure and see if it gets us anywhere or where do we get stuck. So the first step of the procedure was to define a ground, a reference potential. I recommend this, unless you disagree. But again, there's nothing fatal will happen if you choose another one, just your life becomes a little bit more difficult. Builds character. Okay, now, going forward, so what do we do? So we have to define the three voltages. The voltages of the nodes, so we can actually define them. That's fine. V1, V2, V3. Again, step 2, so far, so good. Now, step 3 was to write KCLs for the nodes in terms of the voltages. So if you try to just do that, let's just try to do it and see what we get. Just write the KCLs for the three nodes. So let's define this current as I1, I2, I4, I3, and then we should call this, I don't know, IY and IX. Right? So those are all the currents. So if I were to write KCLs for these nodes, what do I get if I just were to write it blindly? So I would get, for this node, I would get, or maybe, oh, let me just do it. This is easy enough for me. I'll ask you for the harder ones. Okay. So for first node, I get that. I1, all the currents leaving the node, plus I4 minus IY. For node 2, I get negative I1 plus I2 plus IX equals 0. And for node 3, I get what? For node 3, I get I3 minus I4 minus IX equals 0. So I can still write them in this form, but nodal analysis requires us to write this in what terms? In terms of the node voltages, right? So some of these, like I1 and I2 and I3 and I4, I have no problem defining them, right? What is I1 in terms of node voltages? It's V1 over V2 divided by R1, or G1 times V1, right? And same thing for this one, same thing for that one, same thing for that one. The problems are IXs and IYs. IX and IY, right? How do we write IX and IY in terms of node voltages? What are IX and IY in terms of node voltages? So how do you define IY in terms of V? Is there a way to do that? No, right? I don't know of a way. If you know, let me know. It looks pretty confusing. So what do we do? So if you have voltages, then, but it's not, all hope is not lost, because what is the ultimate objective of the nodal analysis? To find what? The voltages, right? So if you have this V1 sitting here, what does it tell you about this capital V1 sitting here? What does it tell you about lowercase v1? It's the same thing. You know it's 10 volts, right? So that's an equation by itself, if you will. You can write it as V1 equals capital V1. So that's one equation already. Now, similarly, you can do the same thing for V2 and V3. What can you say? Exactly, V2 minus V3 is equal to capital V2. So two equations. We need, how many do we need though? We need 3, right? So if I purely look at it from a mathematical perspective, and I'll tell you how to do it from a circuit perspective in a second, but let's just look at it from a mathematical perspective. I need one more equation that doesn't depend on Ix and Iy, Ix or Iy essentially, right? Is there a way to get that equation out of these? Because I1, I2, I3, and I4 I have no problem. I can state them in terms of V1 and V2. It's the Ix and Iy. The current through the voltage sources are the problem. Can I get an equation out of these that would do that for me? What is that equation? How do you get it?
Add the last two.
Exactly. Add the last two, right? And eliminate Ix between them. If you add the last two, what do you get? What you get is negative I1 plus I2 plus I3 minus I4 equals to 0. And this is a good equation because I can write this. Negative I1 means basically G1 times V2 minus V1. Okay, so this is good enough for you guys. So let's do it. Who was next in line? Yes. So can you give me the rest of the terms? So I wrote the I1, negative I1 term. So go to the I2 term. G2 times V2, exactly. And I3, G3 times V3, yes. And last term, negative I4, G4 times V3. Well, V3 times minus V1 or V1 minus V3? No, yeah, you have to be careful. Right? V1 minus V3 equals 0. So I have my three equations, three unknowns, right? So I'm doing just purely algebraically right now. I'm not thinking, I'm just doing algebra. I'm using what I know already. So that's a good thing about algebra. You learn it, then you don't have to think about it too much. Just follow the process. It allows you to think about other things when you do that. So I can write the matrix. So the first line of the matrix, so tell me what the first line of the matrix is using this equation. So this is the matrix times V1, V2, V3 that produces the stimuli vector. So what is the first line? So what are the terms? No, it can't be V1. V1 is here. It's the it's the coefficient of V1. Exactly. 1, 0, 0. Right? That produces lowercase v1 equals capital V1. Or you could write 5, I don't know. Or 10, sorry. Now, how about the second line? 0, 1, negative 1. Good. And since you answered quite a few questions, I'll go to the next person for the last one. All right, so how about the last line? Negative G1 minus G4. G1 minus G4. I have a negative G1 here, right? Right? So it becomes a negative G1, and what else has a V1? Yeah, okay, so negative G1 plus G4. Okay, how about the V2 terms? Plus G2. Yes, and then G3 and V3, G3 minus, plus, yes, G4. Excellent. So, and how about here? We forgot to put this here. This is V2, and what do we get here? 0. So this is my equation. I can put numbers in it and try to solve it. Okay, we know how to do this kind of thing by now, so I'm not going to do that, but just you know how to solve this now, right? I mean, everyone should be comfortable with solving this. Now, okay, this was purely mathematical, but this mathematics can be also seen from a physical, kind of like more circuit insight perspective. What did we do, really, when we combined these two equations from a physical viewpoint? I'm going to tell you what we did. You want to think about it for a second? Think about what we did. Any suggestions what we actually did? Okay, yeah.
We combined a node that doesn't have an independent voltage source.
Right. And where is that node? Or does that node exist? Yes.
So is it the combined node of 2 and 3?
Combined node of 2 and 3, right? So what do we mean by that? Let me just, so if I drew a kind of like a box around this box. Now think about this like a little oval as a gigantic node, as a gigantic dot. Forget about what's inside for a second, okay? If I were to think about that as a gigantic dot, so this is like a black, I could fill it up with purple, and this gigantic dot. Do you agree that KCL should be also valid for anything, any box, any closed path I draw. It's not necessarily for a node. And the reason that's true, again, goes back to something that we did the first lecture. The fact that there's no net charge accumulation when you have the circuit assumption, when the dimensions are much smaller than the wavelength. You have no charge accumulation. So this inside of this thing cannot accumulate net charge. It can all of a sudden become very positive or negative. Right? So it means that the sum of all the charges that go in, the algebraic sum of all the charges that go in or come out, has to be what? 0. So it means that KCL applies to this. This actually has a fancier name, so that I just will mention it so that you know. I mean, this comes from graph theory. It's called a cut set. This is a cut set. You can actually cut a set. So anyway, so if you write KCL for this giant node, what are the currents coming out of it? It's negative I1, negative I2, oh, I'm sorry, negative I1, positive I2, positive I3, negative I4, which is exactly this equation. Right? This equation describes the currents leaving this supernode. That's what it's called. We call them a supernode. So you could have actually arrived at this by essentially doing that. So you didn't need to, I didn't need to write all these equations and convert it. So, well, okay, I have a voltage. I will define a supernode around it, and I write the currents that go into the supernode. And that gives me the equation I need, because it eliminates the current through, because it really doesn't care what is the current flowing inside that node, that Ix. Right? It becomes unimportant. It's inside the black box. Yes?
Can we make a different supernode with the other voltage source?
Right. The supernode for the other voltage source is simpler, therefore it becomes irrelevant. The supernode for it is like this. You could do it, but what would it tell you? It would tell you that I1 plus I4 plus this current is going to be 0. Since one end of it is connected to ground, you don't need to worry about it. You could define this new current, whatever, IZ, and then write it in terms of that, but then you're adding one additional unknown that you have to deal with through this node. And you've eliminated the advantage of using a ground, a reference. The ground eliminates one equation, right? It reduces the order of the system by 1. So if you do this, yes, you can do it, and you can solve it, but you have basically thrown that advantage away. It's good these are good mental exercises that you guys are doing. These are good, because you're thinking about it. It helps you understand what's happening, why it works the way it does. Okay? It's not just mechanical for you. Good. So we could do that, but it's not going to help us that much. So the two equations are, again, the equations. So these are still valid equations. So what you see, you make a supernode, but what you learn from that supernode is that the node voltage here and there are different. So you know that the difference is V2. So you keep this equation, and you keep that equation, and you generate this third equation. So now you can deal with anything. Now you have everything you need to know to solve any problem. As I said, in the arsenal of all the weapons you can attack a problem with, this is a circuit problem. This is the H-bomb. Right? So it just destroys everything. All right. So yeah, okay. Let's stop here.